Should we start? Yeah.
Okay, let's continue. Good morning, everyone. Today we are very pleased to have Dr. Ruiz and Vinchala with us. Dr. Vinchala received his BS in Electronics Engineering from the Salesian Polytechnic University in Koopman, Ecuador. He earned his MS and PhD in Control Engineering from the Technological Monterey. He was a visiting scholar at Columbia University in Montreal, Canada, and later a postdoctoral fellow with the Climate Change Research Group at Technological in Montreal. From 2020 to 2023, he worked as a full-time researcher in the Department of Mechatronics at Technological in Montreal campus, Guadalajara, Harvard. Dr. Vinchala has extensive experience in applied control engineering. He has led technology transfer projects with the cement industry and the Ecuadorian Air Force. His work includes deploying predictive and nonlinear control strategies in industrial grading circuits, as well as developing advanced automation and monitoring solutions for aerospace maintenance environments, showing his ability to translate theoretical methods into real-world systems. He has authored or co-authored more than 90 indexed publications, including journal articles, conference papers, book chapters, and a book. His research interests include fault-tolerant control, energy system, robotics, automation, and process control, always with a strong focus on bridging advanced control theory and practical industrial and defense applications. Currently, Dr. Vinchala is a faculty member in the Department of Electrical Engineering, Electronics, and Telecommunications at University de Koopman in Ecuador. Now, please join me in welcoming Dr. Ruiz and Vinchala. I will hand the floor over to you.
Thank you very much, Dr. Yu, for the introduction, and thank you, Hyun, for the opportunity of presenting my current results on a relatively recent area of research that I have been leading for the past 2.5 years. So the presentation for today is related to the modeling of nonlinear multiple input, multiple output systems, which is a tremendously active research area in control theory. I will try to highlight mainly the results of the latest of my research, but also the objective of this talk or kind of workshop is to provide you some useful insights into this theory so you will be able to apply it for yourselves. I haven't draft an agenda, so the slides would appear to be infinite for you because there's a lot of mathematics throughout all the presentation. But don't be overwhelmed by what you are going to see. It doesn't matter if you aren't able to gather all the information. I will try to make it as easier as possible so you can understand it. So I come from Ecuador. It is called the country with the 4 visions. We are a small country, actually. All the population from my country would fit in Chongqing because we are only 17 million people. But we have 4 regions. The coast, which is near the ocean, a really hot sun. The temperature is high with a lot of humidity there. And also there is the Indian region, We have mountains. Actually, that's the place where I come from. From the mountains, we have the constant temperature throughout the year, and also there is the jungle, magnificent place. And our best place to visit for tourism, the Galapagos Island, where Charles Darwin developed his evolution theory. I particularly come from a city called Cuenca. Actually, this city, as many cities, beautiful cities in the world, has been considered as a World Heritage Patrimonium from the UNESCO. We have a lot of beautiful things to see there, so you are pretty welcome to visit us anytime you want. And particularly, I come from University of Cuenca. It's the public university in our city. We have 6 campuses throughout the city, and I particularly work in a new campus, the technology one, where all the engineering faculty moved 2 years ago. I would like to briefly present my research team. There's many people there. I decided not to put a photo of our lab because our lab is a little bit more modest than the ones you are able to find here in China. But maybe the one of people is of more interest for you. We have 1 postdoc, 5 PhD students of our programs, 4 master students, 2 full-time researchers who are works for us. They are transitioning from masters to PhD students, so we are able to offer them positions, temporal positions, so we can retain their talent with us. 3 full-time professors, including myself, 1 administrative support. It's very little for a lot of work we have to do in administrative things, and 1 visiting student who is going to be with us until September. So these are the guys behind the scenes of what I'm going to present today. So a little background about the problematic we found 2.5 years ago when we decided to start pursuing some specific objective about proposing something different in how to model nonlinear dynamics in multiple input and multiple output systems. So when modeling something, we have different approaches. The first one could be using physical laws approaches, like transforming equations, Newton's second law, either for translation dynamics or rotational mechanics, for instance. Any particular physical law approach would lead us to an ordinary differential equation, mainly with a lot of non-linearities. But since it is a model-based, where from a physical law approach, it is quite typical to forget something or to avoid some difficulties when modeling, and we can have a not that accurate model that it's going to be just a simplification from reality. What is particularly interesting when using these particular models is that we have what is called a white box model. Everything within the model is well known regarding variables. When we transform such a model to a state representation, every state is a physical variable, for instance. And then we could have machine learning approach, or anything related with supervised modelings or something related. This approach is particularly good to model complex dynamics, but has another issues or challenges, such as overfitting, for instance, or the lack of capacity for generalization. Actually, local perspective of non-linearities are typically captured by these models. one of the drawbacks of this modeling approach from machine learning or some approach related is that we end up with a black box model. So what is inside the model, it is not known for us. Of course, we are able to produce the outputs of the signals we are trying to mimic, but a possible steady space model is not physically related to variables from measurements, for instance. A particularly relatively new approach for modeling and doing control is the data-driven approach. This data-driven approach relates taking measurements and trying, of course, to mimic measurements into a non-black box approach, and in order to better present the information, actually the Koopman operator, I'm going to introduce this particular approach in the next slide, allows us to produce what is called gray box models. And this allows us to achieve a spectral decomposition in order to match possible behavior of physical based models with this particular approach. So this is basically what we tried to tackle by using new approaches. I use like the quotes, like new approaches, because when doing the literature review, we found something really interesting. It happens that in the year 1931, Koopman himself, the creator of the approach, published a paper where he proposed to use information from different dynamical systems. A dynamical system we would understand as something or some particular mechanism able to transform one signal into another with system interaction. And took these particular measurements or signals and elevate them into an infinite space, which is called the Hamiltonian space. So imagine something. You could have a highly nonlinear system with a lot of complexity. If we were able to see this system in a state space representation, and for making it easier, let's assume we have a second order model. So if we can imagine a second order model, we would be able to imagine interaction between variables in a plane. What could be able to, actually the name of this plane is the phase plane. So a plane could be something like this particular representation. We are looking at this in this part. But of course, this representation of a plane implying to represent a highly nonlinear system would imply a lot of mismatch, because nonlinear dynamics are not able to be represented by a plane. Imagine complex representations in a second order interaction. It would be something really different from a plane. Something like, I don't know, maybe something super difficult to explain with a particular linear function. If we use linearization, actually what we do is to slide this nonlinear representation and take just a part of all the interaction of the dynamics of the system, which is in the plane itself. But the plane represented this highly nonlinear dynamics would depend on in which part we make the slice. So of course, trying to represent a highly nonlinear dynamical exponential system with a linear one would imply a lot of mismatch, several mismatch. So the key idea of the approach is to use much more variables to represent these nonlinear dynamics. And Koopman in 1931 developed a theory that is really easy to understand. At least the concept. Maybe the mathematics aren't that easy. But the clue concept is that these non-linear dynamics could be represented in a linear fashion, but by using an infinite space. And it makes all the sense, of course, because maybe if we take infinite space, of course, we could put some of the non-linear interaction in one of the multiple extra states we are adding up to our model. So this would be the Koopman operator in a nutshell. I'd say maybe, of course, this could be a new theory for you, but the only thing that we could take as a key concept from this slide would be that this Koopman operator that is represented with this kind of K, it's like a nice shaped K, I would say, multiplying an Asian function from matrices coming from the measurements of the system are able to be operated by this function, Asian function itself, with its Asian values. So I previously mentioned in previous slides, yeah, that the great thing about this approach is that we are able to perform a spectral decomposition. And in this slide, the clue concept is that actually the spectral decomposition is represented in this particular equation. So everything from now on is going to be based on how to achieve a representation, at least something close to this K operator, which is called the Koopman operator, in order to achieve this extended representation for a non-linear system with multiple inputs and multiple outputs. So when we found this approach, at least I myself found it, I got in love. This was the second time in my life when I deeply got in love with something. The first time was with my wife, happily 11 years, also 11 years married. And then when I started to doing some research, literature research about this, well, there is a huge gap from the beginning or the actual definition of the Koopman operator and the development of algorithms for trying to get close or determining the Koopman operator, this one with the K. So in 1931, Bernard Koopman developed this particular theory, and a close collaborator of him, von Neumann, developed a well-defined background about the spectral properties of this operator for describing nonlinear systems with linearized systems. Actually, it is not a linearized version, it's linear systems in an extended domain, dominion. And if you are able to see the gap from 1931 to 2004, it's a lot of time. And I was thinking, why is that it took like 70 years or something like that for someone to start doing some research related algorithmically, I would say, with this fantastic theory. And it happens that, of course, we needed computing performance. And after this paper from Messick, who I would say is the father of the algorithms for the Koopman operator, there has been a lot of message, actually is the right pronunciation of his last name. There has been a lot of contributions regarding its algorithm, but what is particularly interesting about this, it's most of the contributions are related with with autonomous systems. What an autonomous system would imply is the one who doesn't have inputs. And of course, in control systems, we barely work with autonomous systems. We usually use non-autonomous systems, which means systems with inputs in order to make control. What is interesting about these non-autonomous systems is that depending on the inputs, of course, we change its operating point in a state space. And remember the plane that I was previously trying to explain that could be slicing difficult dynamics in order to try to explain something really specific. So in the case of a non-autonomous system, if we use common approaches, even data-driven classic approaches for modeling nonlinear with systems with multiple inputs and multiple outputs, if we learn some dynamic, it would be a local dynamic. And if we turn the operating point far from this previous operation point where we learn the dynamics, we are going to have a lot of uncertainty. And of course, uncertainty means errors. And in control theory, for making good controllers, we would have to apply robust controllers and so on. It would make even more difficult all the approaches for achieving good controllers or good control performance. So, of course, this theory, the Koopman theory, is able to capture all the dynamics in the extended domain without this constraint of not being able to change its inputs because we have different dynamics for a particular learned local model. So we are able to generalize. But these particular algorithms we accept, which should accept control inputs, are not, this area is not completely solved. So if you need some new research topic, here you have something that is a hot spot, I would say, for researchers in control theory. So we made some, of course, contribution based on previous literature review and our own appreciations about this theory. We were able to identify some algorithms for approximating this Koopman operator. Some of them are based in this pretty well-known dynamic mode decomposition. And actually the extended dynamic mode decomposition algorithm is the one who is able to accept control inputs. But it still has some issues. I'm gonna discuss it throughout this, the slides I already have prepared. And of course there is the sparse identification approach as well. I will show you some results in this particular matter. The Cindy algorithm, maybe you heard of it. Some machine learning, this is the upcoming work we are currently performing. And there are other methods, several other. It depends on the literature you find. So our roadmap for estimating the Koopman operator Well, after the literature review and gathering some insights into the mathematical tool and also the algorithmic tool, we tested some of the previous algorithms I showed in 3 different platforms. A multi-tank in cascade system, actually 2 tank systems with 2 heights as outputs and 3 inputs, because we were able to control 3 different input flows within the tanks by oh, sorry, I just forgot the word back. Just by controlling the valves. And we also tried to use this approach in another nonlinear system with more than 1 input, more than 1 output, but this is a sub-actuated one, which is the Fruta pendulum. And finally, we took this really easy testing platform, which has 2 input signals for heating up, 2 actuators, which are really close to temperature sensors, and we have 2 output measurements for temperature, and 2 control inputs for heating up, for changing the heating through the sinks of this board for making some tests. So I'm going to discuss some of the results with this interconnected tank system, and algorithmically speaking, we went through the working process I described here. We have to collect data, to pre-process it, of course, and to try some of the algorithms we developed, extended DMD, CND, or DMD with control. This is like the based on dictionary functions. I will explain what a dictionary function implies. When we know dictionary is defined, we can test different algorithms, such as non-recurrent sets or autoencoders. Okay, so in this first step, with the multi-tank system, we have 3 inputs and 2 outputs. This particular system is highly non-linear, and its dynamics is slow. So these are the core characteristics of this particular system. So we went through the data acquisition, and after that, we applied an extend DMD, an extend dynamical mode decomposition method, in order to find or trying to approximate the Koopman operator. So one of the difficulties in this stage of the research was when we were learning about this approach, for the extension of the variables we want to define, there is not a recipe. You are not able to find an algorithm who says exactly how to extend the state space representation, because since even if you have a second order system, you can have infinite possibilities of state representation even for 2 variables. Or imagine what would happen if you, instead of changing the state representation in the same plane, change the representation by adding more variables. That's even worse, of course. So no one tells you how to extend, how to add up more degrees of liberty or variables in order to extend the representation with this specific approach. But you can guess a little bit, at least with this particular approach, which implies defining dictionaries. Actually, the dictionary is something like this. You try to translate something to give some insight. For instance, in this particular system, as you can see, the states, where are the heights, H1 and H2 are within a square root. So one of the things that you could do is when defining more states, for instance, it could be one extension of the state space. You take the state variables built from measurements, and you could instead of proposing this polynomial, you could use the square root of the measurement in accordance with the model. But that will be the case if you know at least something about the modeling transformation of the system. But what if not? So actually we extended the system by putting a square root of the heights and also some interaction between the heights and interactions by a vector product of the measurements, vector of measurements and the vector of the control inputs. And of course we just apply the dynamical mode decomposition method in order to approximate the Koopman operator. And this is what we got for this system, for the multi-tank system. The closer representation represents something different from the traditional approaches, which is the green line, the dynamical mode decomposition with no interaction with the inputs. Of course, as we can see, the prediction is not quite good. But when we add up the inputs for adding interaction between the states and inputs in order to try to explain the possible change or the change of the state of operation, of course, we get much better results. And yeah, that's something we can check from the time series representation. But as I mentioned at the beginning, one of the strengths of this approach is that we are able to provide spectral decomposition. What a spectral decomposition would imply, of course, is trying to evaluate eigenvalues of the function. So in black, I wouldn't say these are the actual eigenvalues or poles of the system, but I would say these are the actual linearized poles of the system. So we took the model, linearized it in a specific average operating condition, and put the poles in this pole and zeros diagram. And as you can see, with the approach, the blue one we are proposing, we get the poles really close to the real ones. But we don't only get closer poles, which is nice because you learn the dynamics of the system. As you can see, we are able to reproduce the dynamic of the system. It can be verified in this time plot because we have a similar fashion in the time series representation. But also, we have several other, the blue dots, several other poles, which are, of course, it's the spectral decomposition we were talking about. What these poles, extra poles, represent then? Of course, the nonlinear dynamics. Huh? You get it? So, of course, we tried to test or to apply a parsimonic approach, getting the less difficult model to represent and the most tractable one, and with the less error possible. So we performed an analysis of the polynomial order in the extension of the model with much more variables and the accuracy. So we had to cut, at least with our search in this particular case, with 5 to 6 poles, I would say. We extended the representation for this multi-task system from a second order one for each tank, no, I mean for the whole system, to a sixth order one. And this is a gray box approach because we know what the poles mean, and we can apply any non-conventional control approach with, which can be used for prediction and also for minimizing cost function where the variables mean something. And of course that was the next step in our journey, to apply an MPC, a model predictive control, to this model. And we tested the model, the MPC, the exact MPC, the same algorithm with the same methodology for doing like the selection of the prediction horizon, the weighting of the weighting within the cost function for the exact same optimizer as well. And we test with a baseline. Of course, the worst case would be like using the linearized system with the NPC, the linearized system with an observer. The observer would be the one in charge of handling the uncertainties of the model in the linearized case. And of course, we use an observer as well with the sixth order we obtained with the Koopman operator with the extended DMD approach. And we just made these two algorithms in this case with the controller working to work, and we put it in a comparison with some errors. And as you can see, our Koopman algorithm works much better. For instance, at 3,100 seconds, we applied, or around this time, we applied a perturbance. So we were able to produce a leak in the tanks. So the system had to compensate the leaks, of course. And the linearized model with the MPC, of course, compensates this particular change in the system, but took some time in order to make the compensation. In our particular case, since we imply we are getting to know much better the dynamics, and the prediction also is going to work much better. And as you can see, of course, the controller also performs much better. Our next step, and at least in this case, was to try proving this approach in something related to fault detection. We haven't done it yet, but what we did at that time was to make both models to run open loop with no observer. And as you can see, the models were like the one with, well, actually the Koopman predictor is the one in orange, and the other one is not Koopman prediction. And when a fault, leakage in this case, is active, as you can see, the Koopman operator is able to, in case we are calculating a residual for fault detection or even diagnosis, of course this residual in the tank where the leakage was established it's like completely going away from the dynamics of a tank, a healthier tank with no leakage. And then we tried to apply the same approach, the extended mode decomposition, but to a different system with a different dynamics. The previous one had several inputs and several outputs, and its dynamics was slow. It was slow. And now the next step was to take something different. We took this flute pendulum, whose dynamics is really fast, or are really fast actually. And it is of course highly nonlinear, and additionally this system is self-actuated. So we have 2 degrees of freedom as output and just 1 control input. So we applied this exact same approach as the multi-tank system, but unfortunately the results were not good at all. As you see, we got something, but this something was nothing useful. We got an unstable system. And then, of course, this should have a solution. Everything in life has a solution. So we were looking like in a different direction in order to be able to provide at least a partial solution to this problem. So we tried something different. And what was different to change the dominium of the approach? We, instead of proposing a dictionary by ourselves, because the dictionary was like, okay, I would have this state as a square root of the measurement and this other as the square root of the measurement as well, and so on. But it is like trying to find something in a huge space, and no direction is the correct. So it's just like trying to navigate without GPS. And in this particular case, the Cindy approach, because in this case, for this study, when we didn't have good results, the extension was made by using trigonometric functions within the states, which of course seemed to be correct according to the previous approach we tested in the multi-tank system, because our intuition said, okay, if the measurement from the model for the extension should be like the square root, maybe here is something similar, because if you see the dynamical model from ordinary differential equations for the fluid pendulum, you have sine and cosines operating in the states of the system. So it seemed like quite obvious to apply something similar in this case, but that wasn't the case actually. No good result. And we changed approaches and tried to automate the search. So of course the algorithm should be different in this case, and instead of performing the optimization in just 1 layer, just as before, we did it in 2 layers. With one particular layer trying to solve a similar problem as the previous one, and the second one trying to reduce distances of the Asian values that are within our searchable space defined or constrained by ourselves. That should be like Asian values that would lead us to I would say a stable system. And for doing so, we defined hyperparameters. So the second layer performs a hyperparameter search. And in this case, we got such I would say, decent results. Because these results aren't like the best of the results I've seen in nonlinear dynamics parameterization and so on. But of course, for prediction, as you can see, when comparing the time series signals, it still depends on the control input. Because when the control input performed like really gently, we were close to the real state, but when increasing the control input to the system to making it like pendulating, we got farther from the real ones. This could be correct by a Koopman filter, for instance, in order to apply this to a controller, but we are not happy with these results, of course. This work is still ongoing, something to be solved, I hope really soon, or I don't know, maybe it's unsolvable, at least for us. But this is an open question still for us. And then the third case was, okay, we tried the dictionary-based approach where we propose ourselves the dictionaries. The second one was to make the optimization in 2 layers, so in somehow we optimize the dictionary definitions. And the third approach we have tested is to use no dictionaries at all. So just let different algorithms allows us to define how the extensions should be defined. And this is the test, the approach reported in the paper of Message and Corda in 2020 from non-recurrent sets approximation. And we test this one. Actually, what is nice about this thing is that we can define like every set of measurements we use can evolve over time. So just as a dynamical system would do with a differential equation. So actually we tried this approach, put it into to approximate the Koopman operator for a different system. In this case was another MIMO system for this thermal plant with 2 inputs and 2 outputs. All of these approaches have been experimental, tested with real signals. And the results we got are quite encouraging in order to make control and to explain difficult systems with quite accuracy. But in addition, this coordinate message algorithm is enabled to be applied directly when you have systems with noise, because noise leads the system to finding spuriosation values, and of course that could lead even to unstable control systems. So we had to filter it, this system, but you know, if you filter something, you can add up dynamics, so you need to define a filter that wouldn't do such a thing. One particular one that is quite recommended for doing that task is the Hankel matrix filtering based approach. And then this is just the algorithm of these non-recurrent sets. And we were able to find the approximate dynamics by doing the evaluation of the spectral placement of the zero and pole diagrams. We got close, really close to the poles of the dynamical system. Of course, the extra poles, as you can imagine, represent the nonlinear dynamics. So we have really good predictions, but again, I have 2 pairs of predictions here. The first one that looks a little bit far from the real predictions in comparison with the results on the right are because the initial conditions of the system were different in the left one and then in the right one. And this is interesting because this approach was primarily based or defined for chaotic systems. You know, chaos depends on initial conditions, so you can completely explain something. And this is also another open research question for us, because we haven't been able to correct the initial condition bias that could result from applying this particular algorithm for explaining nonlinear MIMO systems. But the results are quite good when applying this to control systems. We also had an MPC. Actually, I would say MPC was my first love. My complete PhD thesis was based on MPC, non-linear one, non-linear MPC. So that's why it's my first love. So the results for this control system were just great. Actually, we are really proud of these results because we were able to apply something that took quite time to be digested, intellectually digested by ourselves. And if you see it like the web page, you would say this MPC controller acting with this linear system identified with the Koopman operator would be actually a non-linear MPC. And that's quite interesting because a non-linear MPC is a good thing in control theory. So the ongoing work for trying to solve all the still open questions we have in research is using autoencoders. As you probably know, an autoencode tries to explain a signal by itself, but with no supervision. In order to, why we are trying to do this? Because by explaining the signal by itself, we can try the autoencoder to be expanded to a different dimension. That's something we are trying to achieve. Some previous results of using the autoencoder for this particular approach for the same thermal process, we have like decent results, but not still useful with good spectral result as well. But this work is still on progress. And some results, I would say scientific results. The scientific results according to this research, the first one of all was a conference paper which was a systematic review performed by Marcos Villarreal. He is one of the team members. He is my former master student. And then with Huiyan, we published a paper in the Journal of the Franklin Institute. It's control based on the Koopman operator, a comprehensive review. I wonder if you want to get a good deep insight in this theory that I've just presented. This is a 48-page paper, very well detailed, that I quite recommended it for you to read if you want more context about what we have discussed today. And the recent publication also from Marcos, I'm mentioning Marcos because Marcos applied for a PhD scholarship here at CTBU in order to be working with Huiyan, and apparently he got accepted. We still don't know for sure, but maybe he would be here in the meantime. And we also have some work under review. This one is particularly interesting because our dream was to be able to get to any industry and to say, hey, I would like to model your process. And how is that possible? No, you just give me your data set from the SCADA measurement and I will do the magic. And actually this paper is trying to do the magic on a real data set of a cement industry closed winding process, and we were able to do it. So I'm very proud also of this result. Independently of the review process of this paper, what I really want to do is to produce an algorithm capable of doing something really useful for industry. That's the goal. And also for the non-recurrent sets that I just presented, we have also another paper under review. So hopefully we will have good news soon, or bad news. I don't know. It depends on the reviewers, especially reviewer number 2, as typically it's sitting here. So that's my presentation for today. Thank you very much. Before ending up the presentation, I would like to ask something to you. Two simple questions. The first one, what's the name of the city where I come from? Does anybody know?
We have a bit
In Spanish.
Yeah, you said it. Cuenca, yeah. I have a small gift for you. Because of the answer. Oh, actually, this is the monument in Ecuador for which represent. Maybe I forgot to mention at the beginning of my presentation that Ecuador is in the middle. Well, actually, isn't in the middle of the world, but it is known as the middle of the world, at least with the two hemispheres, because we are at the latitude 0. So you are able to visit Ecuador. There is this monument in a small town called Mitad del Mundo. It would be like the middle of the earth. The second question is like, what is the name of the operator we mentioned throughout this presentation?
The Koopman operator.
Yeah, but I cannot give you the present because you are from Ecuador. No, I cannot give you this one, Victor, because this is for foreigners. But thank you very much. Okay, let's go with a kind of difficult one. What is the name of the algorithm I use it? Maybe any of the algorithms.
Machine learning, data driving.
Anyone? But it was like dynamical mode decomposition, part of it, and so on and so on. But I'm gonna give this to anyone who is interested in having a small souvenir from Ecuador. I don't know how to. Yeah, you can have it. This is Diablo Uma. It's a special character from our culture. And actually, I really like this souvenir. I already gave Ho Yang some souvenirs from Chile. And with no participation at all, I'm gonna give Dr. Lee a little souvenir from Ecuador as well.
Thank you, Professor.
I'm welcome.
I have a question.
Of course, yeah.
I have a question too.
I found today's discussion on the Koopman operator very interesting, especially it can be used to do some black box control problem for nonlinear system. And trajectory control precision for the interconnected consistent my own research focus on reinforcement nonlinear control, adaptive control, optimal control, neural network, and nonlinear control. So I'm also very fond of data-driven control method. Will you please say a little more about the data-driven method based on operator?
About data-driven?
About the data-driven method based on operator. Yeah.
Well, I would say the data-driven area is quite wide. As Dr. Lee mentioned, data-driven can be applied to modeling and for control as well. What I did was particularly data-driven for modeling. What is the difference between data-driven for modeling and, as maybe you know, you can also use time series modeling by using data. This could also be called data-driven modeling as well, but it's closer to the approach of system identification. And also you can use data for training black box model in order to get, of course, system identification. But why this is particularly called data-driven modeling? Because when you model, you usually get something that you can understand from beginning to end. And that's actually what I said at the beginning, that the physical laws approach provide us white box models. And that's particularly good because if you are able to know every state within a system or a model, I would say, you can achieve better when doing control, for example, or when doing predictions. In the case of black box models, if you are trying to apply this to control, I would say it's like trying to control something with blind eyes, because the only thing that you consider for getting better control performance is trying to minimize indexes, such as the error or anything else related in a cost function. But when you have gray box models, you could understand what is almost everything within the model, especially because you are composing the vector of the system with the measurements themselves, and also with some representation of the measurements, or even if you don't know how the representations in the signals are being treated in order to get the extension of the model, at least you know a part of all the vectors. So that's really good because you can, within a controller, you could constrain some specific states in order to achieve better. So you would be able to achieve objective-oriented control with such modeling. So that would be like the model-based control. I'm sorry. That would be a bit of an explanation of data-driven modeling. Now, if you try to apply a similar approach, but for controlling or for controllers directly, which is data-driven control, you would skip the modeling process. And what you would do is go directly to develop controllers by using data. Now, I haven't stepped into this area yet, but I hope to do it soon. Yeah, and if you are, of course, working on that approach, I would love to get a little bit more of cooperation with yourself.
Thank you.
So thank you very much for the interesting question.
Thank you, Professor. That's very helpful for me. I also think the traditional model identification of is hard to get a high precision. Yeah, so I like data-driven method.
Great.
Yeah.
Great.
I also think in the future maybe we can cooperate in this control idea.
Great. It will be a pleasure.
Thank you, Professor.
Thank you very much.
Now,
Now, there is another question from
Yeah.
Victor.
Yes. Imagine a multivariable system with 10 inputs and 10 outputs. As you will get a Houston function that captures all the dynamic of the nonlinear system to make it linear. I find it an interesting challenge to obtain this adjustment function for highlight nonlinear system and with a large number of inputs and outputs, since the quality of the model will depend on how good this adjustment function is. How do you say?
Well, what I can understand from your question is that you have a 10 input, 10 output non-linear system. It doesn't matter what system is, because this could be applied to any dynamical system. And what I also got from your question is that it would depend the accuracy of the model on a loss function during optimization. Is that correct?
Yes.
Well, in this particular case, you have a lot of algorithms. What I presented today was particularly 3 approaches for trying to identify, or say, to get a close representation of this K operator,
Okay.
which is called the Koopman operator. Okay, so in this particular case, of course, if you want to represent such complex dynamics, you will have to extend the representation from a 10 order state system to a much higher vector or state representation. I wouldn't know what would be the final dimension for getting an accurate representation. Of course, that needs to be tested algorithmically and to try to get some good results. But definitely this approach, independently on what of the methods you use that were discussed throughout this presentation, could give you a good approach. For instance, the first one was trying to define by ourselves the dictionary. In the case you know some insights about the system, you could imply that maybe if you have 10 measurements, maybe the state number 11 would be like the square root of state number 1. And maybe the state number 12 would be like the multiplication of state number 2 and 4 and so on and so on. But that's like going blind in a huge space and trying to find something difficult to achieve. But because we knew some insights in the multi-time system, we were able to particularly apply this approach in this case. And the results were, okay, very good. It worked. When we tested a more challenging system, actually this system is far from your reality from 10 by 10. It is just one sub-actuated control input with two outputs. We tested exactly the same approach, but of course the results were awful, not useful at all. So we had to change approaches. And the second approach isn't just a matter of evaluating a cost function or a loss function by itself by doing the optimization in 2 layers, because we have the optimization layer, the simple one I would say, and a second one which tries to select a hyperparameter which is defining the dictionary, which is not being defined manually as the previous approach. So in this case, as you see, we are trying to compare the distances between certain measurements, as it can be seen here, after the first level of the optimization. So in this second level, we make a second optimization, and of course we try to obtain. The goal is the same, to get this state matrix in order to have a linear system capable of explaining the highly nonlinear dynamics. In this particular case, we got decent results, at least a stable model, but in the case we change the amplitude of the input system, as you see in the results, we get, of course, some different results in the model performance. And the third approach we tested it is non-defined dictionaries at all, this is just going with recurrent sets. So think of a set. You can compose a set in any multiple, infinite possibilities. You can do it by several possibilities. You can do a set like, I can group this object and this object as well, and this object, and I will try to making it evolve over time. And I will see how good it goes. Maybe the result is not good, so I will perform a set like this one. And maybe this set of course doesn't evolve well as well, so I will try to make like this and this, and so on and so on. So it's another optimization approach, but everything is based in the same principle. And there are, I would say, different ways to do this. What we are trying to do now is to try to explain the signal by itself with an autoencoder in order to see how to extend the dynamics, how to be advised in the extension of the other states of the approach. So that's like, what could I say about you?
Very interesting, thank you so much.
Oh, thank you for the questions and your attention, and I hope you didn't get that bored during this presentation. Actually, I love presenting something. It's the first time I do this presentation with these details. I usually have a lighter version, which I use for friends. But since you're all academics, I decided to include more detail. Thank you.
Thanks again to Professor Zhang and Professor Michala, and thank you all for your attention. That concludes today's session.
Okay, great.
Okay, thank you.
Yeah, a picture, it would be great. Maybe I can project the slides for a picture. Can we join for a picture?
Yes.
Welcome. Thank you very much. Let me pause the video.